Okay, so welcome to this next video in the playlist on functional analysis. So in this video what we're going to do is we're going to look a bit more in detail at limits in the L-infinity space, and we're going to do this as sort of like a forerunner to proving that the L-infinity space is in fact a complete metric space. Okay, so let's suppose, so we're dealing with, well, firstly we're dealing with the L-infinity space, which is the set of all sequences, so it's a set containing sequences, so the elements of the set are now sequences. So let's say X is a sequence, X1, X2, X3, etc. And all the terms of the sequence are either real or complex numbers, depending on whether you're dealing with the real L-infinity space or the complex L-infinity space. So the xi are either real or complex numbers. Okay, so we'll stick to the general case of these, so we'll just say everything we will do will work for both real and complex numbers, so it won't matter basically. Okay, and these sequences are bounded basically, which means that the supremum over I is an element of the natural numbers of the modulus of xi should be finite. So there should be there should be some number which is a real number which is greater in size than all of the terms of this sequence. So it's a bounded sequence of real or complex numbers, which means in the case of the real line that it's completely contained within some interval of size big M around 0, or in the case of the complex plane it means that it's contained within some disk of radius big M in the complex plane. Okay, so all the terms are basically of the sequence are within here somewhere, but they don't need to converge. These sequences do not need to be convergent. Similarly, if it's a real L-infinity space, they're all in here, but again it doesn't need to converge. It could be the sequence flipping between 0 and 1, 0 and 1, 0 and 1, which we know doesn't have a limit. Okay, and then that's just a set. So the way we converted it into a metric space was we put the d-infinity metric on it, which is defined such that the d-infinity of two sequences, let's say x and y. So remember, x and y are whole sequences of real numbers or complex numbers if it's a complex L-infinity space. So we've got x1, x2, x3, x4, etc. like that. And we've got y, which is also a sequence of real or complex numbers, which is an element of this sequence, which means that this supremum, they are both bounded sequences basically, a y2, y3, etc. as well. And basically we define d-infinity of x and y to be the supremum over I as an element of the natural numbers of the modulus of xi minus yi. So basically you could think about defining a new sequence which was x minus y, which would be all the terms of this sequence subtract their corresponding term in this sequence. So we'd have x1 minus y1, x2 minus y2, x3 minus y3, etc. And then all you're doing is taking the supremum of all these terms basically. So put them all into a set and take the supremum of that. So when I write, oh well, you actually take the modulus of them, sorry. So you're taking the supremum. When I write the supremum over I as an element of the natural numbers, the modulus of xi minus yi, what I really mean by that is the supremum of the set containing the modulus of xi minus yi, where I is an element of the natural numbers, basically is what I mean by that. Okay, so we've shown in previous videos that this is a metric space. That firstly, if these two sequences are elements of the L-infinity space, and I should have written that, this is an element of L-infinity and this is an element of L-infinity. If they are both elements of the L-infinity space, then x minus y is basically also an element of the L-infinity, which means that this supremum is a finite value, so it's not going to be infinite basically. So it's well defined, and we've proven that it obeys the axioms of a metric space basically. Okay, so what we now want to do in this video is discuss more about what it means to converge in this metric space, and some properties, for instance, well, what we want to work out is its relation to convergence in the real line. So we've seen in previous videos that the complex numbers, if you're taking the limit of a sequence of complex numbers, it's going to converge to exactly what basically you can split the sequence into its real and imaginary components and take the limits of those two real sequences and basically just add them together with remembering to add the imaginary part to the limit of the sequence of imaginary components, and the whole sequence as a whole will converge to that. So it's very much so related to you can reduce the problem of finding the limit of a sequence of complex numbers down to finding the limit of a sequence of real numbers, and we want to be able to do a similar thing in this case. We're not going to be able to do as well in this case, but basically what we'd like to do is be able to take a sequence of sequences and say that it's going to converge to what the terms converge to pointwise. So let me just tell you what I mean by that. So if we've got another... Yes. Okay, right. So, if I have a sequence, let's say S, which is a sequence now of elements of L infinity. So we have S, which is S1, S2, S3, S4, etc. And these are now not real numbers, not complex numbers, but they are entire sequences. So this is these are all elements of L infinity, basically. So if I write them out, S1 is some sequence. Shall we denote it X? And I'll put a superscript to denote that this is the S1, so X1, and this is the first term of the sequence S1. So then we've got X1, the second term of this sequence S1. So the superscript is there to denote this subscript over here. So the superscript 1 denotes that this is the sequence corresponding to S1, and these subscripts here denote what term you actually are of the sequence S1. So then we have X1, 3, X1, 4, etc. And these are all either real or complex numbers depending on whether we're dealing with a real L infinity space or a complex L infinity space. Then S2 is equal to some other sequence, X. Now I'll put the superscript 2 to denote that this is the sequence corresponding to S2, and then 1 down here for it's the first term of this sequence. Then we'll have X22, X23, X24, and etc. And then if we go on, we'll just put one more. We've got S3 down here, which is the sequence X31, X32, X33, X34. So the superscript denotes that it's the sequence corresponding to S3, and the subscript denotes what term of the sequence. Oh dear, what's happened there? That should have been a 4. And what term of the sequence you are. Okay, and then we can go on and on and on and on and on. Okay, right. So basically, what this is a sequence of sequences of real or complex numbers. So it's getting more complicated, basically, and functional analysis is all about these things. So get used to it. Right. So what we're now going to ask is, what does it mean to converge in this metric space? What does it mean to say that this sequence converges to, let's say, what should we say it converges to? We'll say it converges to a sequence L. So it converges to an element L, but remember, L is not a complex number, it's not a real number, it's a sequence of real or complex numbers, so it's an element of L infinity as well. Okay, so what does that mean to say that this sequence converges to L? Well, it means exactly what it means in an abstract metric space. So let's just recant the definition in an abstract metric space. It means that for all epsilon greater than 0, there exists some big N, which is an element of the natural numbers, such that if little n is greater than or equal to big N, it implies that the distance between s little n and the limit L is less than epsilon. So basically what it means is that I can find you some point in the sequence, some s big N, such that if I take any term s little n, which is beyond that point in the sequence, then the distance between that term s little n and L is going to be less than epsilon. But what does the distance mean? What is the distance in this metric space? It's the d-infinity metric. So this distance between Sn and L is, if we just replace d-infinity with what it is, it's the supremum over I is an element of the natural numbers of the modulus of Sn minus L. So let me draw out what that means. So this sequence of sequences, if we're going down like this, it's converging to some limit L. So I'll write out this sequence. Let's say this is a sequence L1, L2, L3. So this is, I'm writing L now out as what it is. It's a sequence of real or complex numbers. So these are the terms of the sequence: L1, L2, L3, L4, L5, L6, L7, L8, etc. like that. And basically, if we take some arbitrary term in this sequence of sequences, so we've got some Sn here, then that is a sequence of terms. So if I use the same notation up here, I get that this is the nth term of this sequence. So I put superscript n, then it's the first term of the sequence corresponding to Sn, and then we have xn2, xn3, xn4. Right. Okay. So, and we've also got some S big N here, which I'll write in to make this to make it complete. So we've got S big N1, X big N2, X big N3, X big N4, etc. So what we've done is we have said, okay, we found this big N, and we've taken some point S little n, such that little n is greater than or equal to big N. And if you take any sequence beyond S big N, then the distance between S big N and this limit L, this sequence L, is going to be less than epsilon. And the distance between this sequence and this sequence is the supremum of oh dear, what have I put there? No, that's not right. Okay, right. So it's the supremum of the terms x big little n I minus li is what I should have written there. So basically, that's just the definition. So if I have the difference between two sequences, x and y, remember, the distance in the infinity norm, sorry, in the infinity metric between x and y is equal to the supremum over I is an element of the natural numbers of the modulus of xi minus yi. So basically, you need to take the ith term of this sequence, which is, this is the sequence here, the ith term is x little n I, so that's what I've done here, and you need to take the ith term of this sequence, which is li, and then take the modulus between them. So this is equal to the supremum, if I write it out as what it exactly is, of the modulus of xni minus li, where I is an element of the natural numbers. So basically what you do is you go along this sequence, you take the modulus of the difference between each one of these terms. So you start off with the first terms, you take the modulus, put that in the set. You then go along to the second one, take the modulus of the difference between them, put that into this set, and go on through every single term, and then you take the supremum of that set. That is what we mean by the distance between this sequence Sn and this sequence L. And we're basically saying that that is less than epsilon. Now, if the supremum of this set is less than epsilon, that means that for absolutely every single term you can think of, the modulus of xni minus li must be less than epsilon. So for all terms, so if I take a specific term, so for instance, if I take xn1 and I subtract l1 and I take the modulus of that, that must be less than epsilon, because if I take absolutely every single one of these terms, so I take xn2 and I subtract it from L2, take the modulus of that, put it into the set, and I go along absolutely every single term and take the supremum of that set, it is less than epsilon. So that implies that every element of the set is less than epsilon. So all of these elements of the set, which was this, every term of this sequence Sn, subtract its corresponding term in this sequence L. If I take the modulus of that difference, that has to be less than epsilon. Okay, and that's going to tell me something interesting, because this is true for all little n is greater than or equal to big N. So if I choose any sequence that is greater than or equal to big N, and I take any s little n that's greater than or equal to big N, and I go along this, and I take the first term, let's say, of whichever sequence it is, and I subtract it from L1, and I take the modulus of that, that must be less than epsilon. So this statement is true for whatever little n you choose, bigger than big N. So basically, what we can do is, we can say that if we just look at this now, if we construct a sequence from this sequence of sequences, so if we can look at the sequence of first terms of these sequences, so if we look at x11, x21, so we're fixing the subscript now, we're saying look at the first terms, x31, x41, then my claim, oh dear, this is getting confusing because I'm putting the commas in as well. Let me highlight the commas in a different colour to emphasise that they are not the subscript. Okay, there we go. And you go on, then this sequence basically must converge to L1 is my claim, basically. Why? Because what's the definition of convergence? The definition of convergence, this is a sequence of real or complex numbers now. So the definition of convergence says that you give me any epsilon, so for all epsilon greater than 0, there should exist a point, a big N, which is an element of the natural numbers, such that if little n is greater than or equal to big N, it should imply, greater than or equal to big N, it should imply that the absolute value of x, let's say little n 1, minus L1, should be less than epsilon. So I should be able to find you a point, x big N 1, such that if I go beyond that point, the modulus of the difference between this term and the limit is less than epsilon. So if I take any term x little n 1 over here, the modulus of its difference from the limit should be less than epsilon. And remember that this modulus function in this supremum definition, if obviously you're dealing with the L infinity space, which is a real L infinity space, this will just be an absolute value. If it's the complex numbers, it'll be the complex modulus function. Of course, they coincide so beautifully that it doesn't matter for our purposes. But basically, this will either be a sequence of real numbers or a sequence of complex numbers. If this is a sequence of real numbers, then this will be an absolute value sign. If it's a sequence of complex numbers, it will be the complex modulus sign. But it will be the same corresponding sign as corresponds with this this definition up here, basically. So if you're using the absolute value here, you'll use the absolute value here. If you're using the modulus here, you'll use the modulus there. Okay, so this is obvious, because if I just use this big N from up here, if I say, okay, what we know is that this sequence of sequences converges to L in this metric up d infinity here, which means that I can find you some big N, which is an element of the natural numbers, so this big N here, such that if you go beyond that, if you take any sequence beyond that, this supremum of this set of distances, of moduluses of the terms take away the terms of the limiting sequence, this has to be less than epsilon, which implies that the distance between any term and the limit and the limiting term is less than epsilon. So basically, it's this that allows us to do that. Basically, this big N, you make this big N the same big N as you had up here. For your epsilon. So basically go along, find this sequence, and I guarantee you that the distance, the modulus of this term, x little n I minus li, has to be less than epsilon, providing little n is greater than or equal to this big N. And the reason is that because the d infinity of the sequence Sn to the sequence L had to be less than epsilon, then that implies that this supremum of this set had to be less than epsilon, and that implies that all the terms of this set had to, all the elements of this set had to be less than epsilon, and the elements of this set are the distances of these terms from the limit. Okay. And this holds for any n, any little n you choose that is greater than or equal to big N. So this implies that this is less than epsilon, providing little n is greater than or equal to big N, basically. Okay, so, and there was nothing special about the fact that we did this for the first terms. We could have done this for the row of second terms. So we could have done it for this this column here. Sorry, not row. This column here of second terms. Again, we could construct the sequence x12, x21, x22, sorry, x32, x42, x52, etc. And again, this is going to converge down to the limit L2. The reason being, if you want a point in this sequence, if you want some x big N2, such that if you go beyond that point, if you take any term in this sequence beyond that point, so any x little n2, and you subtract it away from L2 and take the modulus of that, you want that to be less than epsilon, I can find you a big N, because just go here, say, okay, this sequence converges in this d infinity metric, so I can find you a point in this sequence, some s big N, such that the distance from any term of this sequence s from the limit is less than epsilon. But once you've done that, you're done, because if the distance of any sequence Sn from the limit L is less than epsilon, then it implies that the modulus of this term, any term in the sequence, subtract its corresponding term in the limiting sequence, is also less than that epsilon because of the definition down here, because the definition of the distance is the maximum, if you like, the supremum of all the distances of the terms from the terms of that sequence from the corresponding terms in the limiting sequence. And that is true for all little n greater than or equal to big N. So all of these terms onwards in this green sequence will be such that their modulus, the modulus of their xn2 minus L2 term is less than epsilon, basically. So what I want to say, what the overall result of all of this is that if this sequence of sequences in L infinity converges to some sequence L in L infinity, so here's this sequence that it's converging to, if these sequences do converge in the D infinity metric, then if you take the sequence of terms, of first terms, so all of the terms of this sequence are sequences themselves. If you take the first term from this sequence, 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 etc., if you take all the first terms and you put them into a sequence, then that will be a sequence of either real or complex numbers. And what I've shown you, basically, is that that sequence will converge to the first term in this limiting sequence over here. Similarly, if you take whatever term you like in here, if you take whatever term you like, so if you take the ith term of this sequence, 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 you take all the ith terms of each of these sequences, that again will be a sequence of real or complex numbers, and that will basically converge to the ith term of the limiting sequence over here. So that is what that's what I want you to see. So it's just like in the case of sequences of complex numbers, except that now effectively you've got an infinite number of terms, and they could be real or complex numbers. And so you've just got loads and loads of terms. But again, just as in the case of the complex numbers, where if a sequence of complex numbers converged to another complex number, it meant that if you take the real component of each complex number, and that's a sequence of real numbers, that will converge to the real component of the limit of the sequence of complex numbers, basically. So I think that's enough for this video. In the next video, what we'll discuss is that the converse, unfortunately, does not hold. That if you have a sequence of sequences like this, and all of these, if you look at the sequence of first terms, and that converges, and the sequence of second terms converges, and the sequence of all the individual terms converge, that doesn't necessarily imply that in the D infinity metric this sequence of sequences converge. And I just want to introduce a tiny bit more terminology before we end this video. This concept of if you have a sequence of sequences like this, of real or complex numbers, and just taking the limit of each of the terms, that's quite an intuitive way of taking the limit of a bunch of sequences, isn't it? You look at the limit of the sequence of first terms, you look at the limit of the sequence of second terms, you make that the second term of the limit, you look at the sequence of third terms, you find its limit and make that the third term of this limiting sequence. That is known as pointwise convergence of sequences. Pointwise convergence of sequences. And what we've proven in this video is that pointwise convergence of sequences. I'll just finish writing that. Okay, and what we've proven in this video is that if you have a sequence of sequences which converges in D infinity, then they converge to the same thing. They converge basically to the same thing as if you analyze it with pointwise convergence. So they converge to their pointwise limit, if you like. However, what we're going to show in the next video is that not all sequence of sequences which have a pointwise limit do converge in D infinity. So the converse doesn't hold true. It's not the case that the set of all all sequences which converge pointwise. It's not true that all sequences that converge pointwise will converge in it's not true that all sequences of sequences which converge pointwise will converge in D infinity. So basically, I could create you a sequence of sequences like this, for which you can analyze the limit of the first terms, you can analyze the limits of the second terms, you can analyze the limit of the third term. But this new sequence you construct, this thing you hope is going to be the limit, actually you can prove it isn't the limit in D infinity. So basically, if we have the set of all sequences of sequences which converge pointwise, there's a subset of them which is the sequences that converge in D infinity, basically. So all sequences which converge in D infinity do converge to their pointwise limits. I'll write this pointwise. But not all the sequences which converge to their pointwise limit do converge in D infinity. Okay, so we'll see that in the next video.